Before proceeding on to section 2.2 and 2.3 in this lecture, I wanted to bring the bottom of page 33 to your attention from the ECE 301 workbook. Having just determining equivalent resistances from series and parallel arrangements of resistances. It's a very common to see, for example, series circuits represented by light fixtures, such as Christmas lights. Sometimes you'll see them. But very importantly, if you wanted to distribute power from a single voltage source to various what we call loads, you would definitely place those loads in parallel. A load typically is a circuit element that is absorbing power, such as a resistance. Because keep in mind that voltage, that magnitude of voltage is equivalent across all those parallel loads. So that's a good design technique when you need that power distributed appropriately. So we're going to go now move on briefly to the next section, just to recall a definition we had earlier. In that, again, this is the top of page 34 on section 2.2. We can also look at conductance rather than resistance, because conductance is just the reciprocal of resistance. The typical variable is G rather than R. And what's interesting in terms of determining their equivalences, it's an opposite of what we just have with the resistances. For example, if you have a series of circuit elements and you're interested in getting their equivalent conductances, then you need to take the reciprocal of the sum of the reciprocals. And again, you can take two at a time, like we did for resistances. But if you have them in parallel, then you actually would add the conductances together. So it's completely reversed from what we had with resistances. And it's easy to show that algebraically, simply because the difference is that the conductance G is basically 1 over R, right? So the majority of this lecture is focusing on what we refer to as network analysis using serial and parallel equivalents. So we're going to go through a very detailed example and break it into several steps or stages of how we can resolve every piece of information in terms of voltages and currents across the entire network. Keep in mind, an electrical network is basically comprised by circuit elements connected together through, in this case, we'll look at a closed path. And we use what we call network analysis to determine the current, voltage, and the power, all three components, current, voltage, and power, for every circuit element, right? And this approach is basically to exploit series and parallel combinations where we can, and just to make sure that at each stage of the reduction, we know what kind of relationships are possible, right? So example 10, again, page 34, we're going to apply network analysis, sometimes maybe abbreviated as NA, to the following network. And you can see very clearly there are 3 resistances and 1 voltage source. The voltage source is defined to be 90 volts. So let's go ahead and put that in. And just for the purposes of references and maybe using formalizations of our approach, let's go ahead and label these resistances. It's sometimes nice to do the labeling just because it keeps track of what relationships we've defined before. So we'll call the top one R1. Let's call the bottom one down, the first 30 ohm resistance, we're going to call that one R2, and the 60 ohm, we'll call that one R3. Again, it really doesn't matter how you label them, just be consistent. And so that's exactly step 1, do your labeling, all right? And then from having labeled those resistances, let's look at the first relationship that we can observe, and we can see that resistance 2 and 3, like we did in the previous lecture, are clearly in parallel. Their nodes are connected end to end. And so we can go ahead and replace them by an equivalent resistance. So let's define that as REQ1 as indicated. And because they're in parallel, we will multiply 60 times 30 in the numerator, and then we will add 60 plus 30 in the denominator, and that will give us 1800 divided by 90. And just a quick division, that should be 20 ohms. So the equivalent resistance for those 2 resistances being in parallel is nothing but 20 ohms. So let's go ahead and redraw it. Let's redraw the circuit with this reduction. Again, voltage source, we already know this voltage is 9 volts. We still have this resistance remaining, R1, which is equal to 10 ohms. And we have deduced that those two parallel ones are nothing but this equivalent REQ1, which is equal to 20 ohms. Okay, all right. So that was step one. All right. So we're going to move through the different steps so that, again, our goal is to be able to resolve all voltages and currents for every circuit element. Right. So we obviously see that we can get another another equivalent after this, and I've designed this on page 35 for just to follow the logic. And this is, again, following the analysis, is that we can see R1 and REQ are in series. So therefore, let's go ahead and define that equivalent, and we'll call it REQ. There was no need to call it REQ2, leading to a final REQ, because this is the final equivalent, okay? So in this case, we're going to sum the two, so it's going to be R1 plus REQ1, and of course it's 10 and 20, so we have 10 ohms plus 20 ohms gives us a grand total of 30 ohms. And we'll go ahead and redraw it, just so that we have the reduced form here. A 90 volt voltage source is simply being connected to an equivalent resistance, which we call REQ of 30 ohms, okay? All right, so at this point, we have managed to represent the more complicated circuit, although it's not that bad, right? Just of three circuit elements involved, three resistances, down to a single resistance. Having done that, we should be able to determine, we have two components of Ohm's law. And so we should be able to use Ohm's law. In this case, what we realize is that, let's just go ahead and redraw it again one more time, just so that we can illustrate. We're going to put a current in, that we have this closed, very simple path with one voltage source and this equivalent of 30 ohms. And there clearly is just one current flowing through here, okay? Remember, we had this before. Yes, they're in parallel, but they're also in series. So therefore there's only one current. We can go ahead and label it, just call it IC1, all right? So using Ohm's law, here off to the side, Ohm's law would then tell us that to solve for I1, you would use that voltage, because this voltage is the same voltage as flowing through the terminals of this resistance, right? They're in parallel. And so we have Vs divided by R equivalent. So we have 90 volts divided by 30 ohms. And so we simply have 3 amps, okay? So this is actually telling us that this is the current flowing through that equivalent, and it's also the current flowing through the voltage source, all right? So the current, we can even say that the current through the voltage source, Vs, is, in this case, we've labeled it I1 equals 3 amps, okay? So we know what the current is through that voltage source, right? Okay. So now what we'd like to do then is see if we can go through and compute some other voltages, all right? Again, we've resolved this down in terms of the equivalences. If we want the different voltages from the original circuit, we've come all the way to the inside, we have to go back out a little bit. We have to expand this equivalence back out to where we came from, knowing that we now know what the current through this equivalent resistance and the current through that voltage source are, right? So we go back and reconsider step 1 in the circuit to get to determine the voltage. We're going to determine the voltage through the REQ1, right? So let's go back to step 1, right? Step 1, the reduction had not gone as far as we just had above. Still, we have a 90 volt source. We had R1 equal to 10 ohms, and we had an REQ1 equivalent here, right? Equal to 20 ohms, okay? So again, this is going backwards, so to speak. Why are we doing that? Because we are interested in getting the voltage and the current for every one of the original components. So just briefly, just taking a quick look back, this is the original problem. Our goal is to get voltages on every one of these resistances, for example, okay? So we use what we can with the equivalences, but our goal is to get back originally to the original circuit elements, right? So this is not original one, but it is an equivalent that tells us something about voltage, right? So for example, let's label this voltage V2, and let's keep the polarities in line with the voltage source, okay? All right. And we again know what the current flowing through here is. Again, this is I1, right? These are all in series, so it's still the same current. See, whatever the current was here, by just expanding this back in terms of these are still in series, so it's still the same current flowing through them, right? So therefore, the voltage flowing through that equivalent, according to Ohm's law, is that equivalent, Req1, times the I1 current, right? So in this case, it's 20 ohms times the 3 amps, and you get 60 volts, okay? Right? Now, that's 60 volts flowing through an equivalent resistance. That again is not answering a question about the voltage through the original ones. However, if we look just carefully down to step 5, but that equivalent was the equivalent resistances, right, for R2 and R3. Where did it come from? Well, it came from the fact that those two resistances are in parallel, right? So the voltage that appears across V2 here must also be across R2 and R3 in the original network. Ah, okay. So what we have here, if we made a little table here of current and voltage, right? Right. So we already know that we have 3 amps flowing through the voltage source, right? We have 3 amps flowing through resistance 1, because again, this is still in series. It's the same current flowing here. Nothing's changed. In terms of voltage, right, we now know that both those original resistance R2 and R3 must have 60 volts flowing through them. Okay. Why? Because they're in parallel, so they would share the same magnitude. In this case, because of the polarities lining up, it'll be the same sign as well. So the voltage is preserved, okay? So whatever voltage is flowing through this equivalent is a flowing through both of those, because that equivalent corresponds to the parallelism of R2 and R3, okay? All right, so continuing on, all right, let's go to step 6, all right? So after determining I1 and V2, we still have some other currents to solve for, right? So what we're gonna do is we now need to go back to the original circuit diagram so that we can get these other currents involved, right? So we'll redraw it. Plus and minus voltage source. Again, just 90 volts. R1 is sitting up here, 10 ohms. And remember, we had R2 here. And we have R3, and R2, of course, originally is 30 ohms. And then over here, we have R3, which is 60 ohms. Excuse me, no. R3 was, yeah, about 60 ohms, sorry. Just making sure consistent there, okay? All right, so what do we know? Well, we already know this current, I1, see, because when we did that reduction, that equivalent, that final equivalent was in series with that one. So whatever current was going through that closed loop was what's going through that resistance. So we already have I1, right? And what we have to represent now is, well, we also know this voltage, right? We know the voltage is V2 through that, which is also through that resistance. But these two are in parallel, so there's no reason to assume the currents are the same. Again, same voltage, but not currents. So this current, I1, after it leaves R2, is being split. And we can see that from the diagram. So again, when circuit elements are in parallel, they're not sharing the same current, sharing the same voltage, okay? If they're in series, they're sharing the same current, but not the same voltages, right? So what we can do now is, because we have the voltages in each of these, and we have, because this is V2 here, it's also V2 here, so we can also write it there. We have the resistances, so let's just apply Ohm's law and get those currents. We go to Ohm's law, then I2 has to be the voltage V2 divided by R2. Similarly, I3 has to be V2 divided by R3. Okay. So again, we've already solved for the voltage before, it's 60 volts, divided by 30 ohms for I2. This is 60 volts over here for I3, divided by 60 ohms. So in the first case, we have 2 amps, correct? And then over here, we have 1 amp. Now, this should make a little sense. This should make sense to us, because remember, this current we determined was 3 amps. How can we know that these values that we've gotten for I2 and I3 are correct? KCL. So for example, if we did KCL check, let's just do a KCL, top node KCL. Well, for KCL top node, we have an incoming I1 must be equal to the outgoing I2 and I3, correct? So checks out. So that's the beautiful thing about doing this analysis, is that as you're applying Ohm's law, looking at series and parallels and equivalents, you should be able to get consistent results as you go through, and have more than one way of checking your answer to make sure that the current flow or the distribution of the voltage makes sense. Okay, right? So if we now want to continue on, we could also use, like I said, KVL to check the value of I2, I3, and V1. For example, let's look at KVL. This is just another check. Suppose we wanted to do KVL on the outer loop clockwise. So in the picture, what I'm talking about is we're going to go around this outer loop here, and we're going to go clockwise. So we're going to go this way, KVL, okay? Just looking at voltages on the outer loop, right? So if we do that, we're coming into the negative pole clockwise into the voltage source. So we'd have minus Vs, right? Then we would be coming into the voltage for V1 and then V2. So let's indicate this voltage V1 here, plus and minus here, right? So plus V1, and then into the positive pole for V2, and that has to sum to equal to 0, okay? So what that tells us is that the voltage source has to be the sum of the voltages through these two resistances, which is the same, and the voltages through V1, okay? All right. And I was going to say, we need to go back and look to see if we in fact have those two. Well, if we want to go back and check for V1, we could do that, because I don't think we've done that yet. So let's just go ahead and check values for V1, because if we do Ohm's law for R1, right, we should have that V1 is equal to I1 times R1. In this case, it's 3 amps times 10 ohms. We should have 30 volts, okay, right? And if we check here, we know this is 90 volts. The voltage source, is that equal to the sum of this voltage and the voltage there and the voltage there? Yes, because that's 30 volts plus 60 volts, okay? So yes, we have the voltage V1, and we can see that it's distributed, that 90 volts is distributed where 30 of it goes here, and then 60 across each of those, okay, right? So lastly, what we're going to do is we're going to compute the power, all right? So let's compute the power for each of the circuit elements, okay? Because what we've done is we have the voltages at every resistance, right? We have the current at every resistance, right? And we have the current through the voltage source. So we have everything we need, right? Power. So let's do power for the first resistance, power for the second one, power for the third one, and power for the source. So if you have 4 circuit elements, you should be able to compute the power at each of them. And we know something about the sum, right? We know just from the law of conservation that whatever we get, the sum of those individual resistances, the powers for them, right? Plus the power at the source must be equal to what? Law of conservation energy, right? 0. That must be 0. So that's another check of our values. They have to sum to 0, right? What else do we know? We know that the resistances are absorbing energy, correct? So that voltage source should be supplying. So you should expect negative value of power coming out of that source, right? And positives from the others, or something's crazy. Right? So let's just use a variety of formulas here, because remember, power is voltage times current, and we have all the values. But let's just exploit some of the other formulas that are possible, just so that we're comfortable with using them. One of them is that you can always take the resistance and multiply it by the square of the current. That's one of the formulas, right? In this case, we would have 10 ohms multiplied by the current we showed was 3 amps. That would be squared, and you would get 90 watts. So that would be a positive 90 watts power generated through that first resistance. Second one, different formula. You could take the voltage squared and divide it by the resistance. It's another way you can get power for resistance. In this case, the voltage was 60 volts, correct? Square it, divide it by the 30 ohm resistance. And in that case, you would get 120 watts, positive again. And then finally, the third formula, let's just do this one again. So we know it's the same voltage because they're in parallel, correct? It's just a different resistance. So we get 60 volts squared divided by 60 ohms, right? So this will be less. This will be 60 watts, right? So just looking at those right now, what are we dealing with? We're dealing with is a total, if we were just to sum these PIs, right, from I goes from 1 to 3, we're looking at a total of a positive 270 watts. Now, without even doing any computation, you know what the power has to be here, correct? You're right. That's negative 270. It's got to be negative 270. But let's just go ahead and use the correct formulas that we need to do. Remember, how do the current directions define the formula for power? Well, in case of the resistances, they're all in PRC. They have to be, correct? They have to be to represent the absorption of energy. In this case, the current was flowing this way. In this loop, it was flowing clockwise, and it comes into the negative pole, right? So it is not PRC. So we should put a minus representing the voltage source is not in PRC. And it'll be the voltage source times the current. So we'll get a minus 90 volts was the voltage source given to us times the 3 amp current. And there you go, minus 270 watts. The sum of those wattages is all 0. Exactly what we should have, okay? So the goal of network analysis at this point is to exploit series and parallel equivalents, to roll back each stage of the reduction so that you can determine the appropriate voltage or current, right, that you need for every single element. Remember, sometimes in the cases of parallelism, the voltage at an equivalent, if it was generated from parallel resistances, gives you that voltage you need for those. If you have an equivalent resistance in series with another one, you know the current through that equivalent is the same through this other resistance it's in series with, okay? So you just have to maintain your understanding of the properties of what it means to be in series and parallel with regard to what is shared, whether it be current in the case of series or voltage in the case of parallelism.